Hello, everyone. Thank you for joining us for today's webinar. Topic today is Anycast DNS. I am Eddie Winstead. I'm an engineer here at ISC. I will be your host for this session. So here at ISC, we get asked about this topic quite often. We operate FRoot, one of the 13 root name servers, and we were the first root server operator to deploy Anycast. So we're excited today to share some of our operational Anycast experience with you. So a bit about the webinar itself. It will be 1 hour long. We are recording this session, which will be posted later, and we'll send you a link after we get that posted so that you can refer to it if you like. And also, if you have others that may be interested in the topic, please do forward them to the recording once we send it to you. Everyone will be muted. We do want your questions. So we had some really great questions on the first session. So your task is to beat the first session with questions. So please do enter those into the WebEx Q&A tab, and the majority of those we will answer at the end of the WebEx itself. We should have plenty of time for question and answer. So about our presenter, well, with Anycast, most of the configuration complexity lies on the networking side of things. So for that reason, we have presenting today Jason Lomonaco, who is ISC's Senior Network Engineer. Jason is responsible for ISC's network architecture and design. His duties include network operations for our FRoot and SMSPE Anycast deployments. Jason came to ISC after being a member of the Global NOC team at Indiana University. We're very excited to have him at ISC these days, and we're excited to get some of his time today to talk about Anycast. So with that, I will hand things over to Jason. Jason?
Great. Thank you, Eddie, for the introduction. So today we'll be discussing Anycast and a number of topics. So first we'll go over a basic primer on Anycast, and we'll discuss some example use cases for Anycast. There are a couple impacts on internet protocols that you have to be aware of when you are anycasting something, so we'll go over those as well. And then we'll especially go over our experience with Anycast. Here at ISC, we operate one of the root name servers, froot, and we also operate a service called SMSPE, which we'll go over both in more detail, but both are implementations of Anycast with DNS. And then we'll also have a number of questions that we'll be able to answer. Well, we should have time for a number of questions. So Anycast is simply a method of using the same IP address on multiple servers. Fundamentally, it is a routing scheme. The configuration is far more about the far more about the routers than the servers. The configuration on the server, to give you an example, a sample configuration would be creating a virtual loopback interface, placing the IP address or prefix that you want to Anycast on the loopback, and then on the system, setting up a routing process. So like Quagga or Bird or something along that line to essentially meld your server state with the routing infrastructure. And we'll have some diagrams on that. Next slide, please. To give you an idea on Anycast, we're going to go over a couple different transit methods. Next slide, please. The first of which you're probably familiar with is just simply unicast, where you have one sender and one receiver. So the red dot in these diagrams is representing the sender, and the green dot is representing the recipient, and the yellow dot are other participants that in this case are not CNET traffic. Next slide. This is an example of broadcast traffic. This is typical in a LAN type environment where you have one sender and there are many recipients, and this is regardless of whether the recipients are actually interested in the traffic or not. It is simply a way of blasting out the traffic to everyone. Next slide. And here's an example of multicast. This is where you have one sender and then you have multiple interested recipients. And these recipients will signal their intention to join the multicast group, and then a path is built from the sender to the receiver, bypassing potential recipients that are not interested in the traffic. Next slide. So here we have an example of Anycast, where essentially Anycast is where you're going to have multiple source points. Essentially, where you're going to set up a number of instances of an Anycast service, either in your campus or geographically across the world. And the recipients that connect to each Anycast instance will connect to the one that's close to them from a network perspective. And that can depend on the routing protocol that you're using. I will touch base on that in a moment. Next slide, please. So like we were saying, each packet sent to an Anycast IP address may reach a different server, and that's okay. And the way that this works is, so if you're doing Anycast on a global scale, you'll be doing it with a routing protocol typically called PGP, Border Gateway Protocol. And the various metrics that are involved there are going to be things like local preference, autonomous system path, multi-exit discriminator. These are all basically different knobs that can be used to try to steer traffic where you want to go. And these will determine, based on where the end user is, which Anycast instance they will be talking to. For a LAN or campus type environment where you might be using something like OSPF or ISIS, it'll be something like cost or bandwidth or so on and so forth. And another thing that you must do in the setup of these Anycast instances is on the server we mentioned earlier where you'll put your Anycasted IP address on like a virtual loopback. And that will be the same across all of your servers that you want to Anycast that address from. But you also need to have a unique unicast IP address, for example, on like the Ethernet interface. And this is the address that you use to manage the box, to do zone transfers, things of that nature, since you can't do that to the Anycast address. Next slide, please. So here are some use cases. This is an example of a local Anycast instance where, in this example, we have 4 servers, and they're on a LAN, and there's a router there. And what they're doing is they have their routing process. And next slide. One more, please. And so essentially, you can peer the servers with the routers with any number of protocols. I've mentioned OSPF, ISIS, BGP, but there are others that are available. And essentially, that is what signals the availability of that node. So, for example, that top server were to just lose its power or fail in some way, that node will go offline, and you'll lose your OSPF or BGP adjacency to the router, and the router will know to no longer send traffic to that server. And so the servers are in service. The router in this particular LAN type environment will do flow-based equal cost multipath routing. So essentially it will do some sort of load balancing across the various servers that are signaling that they're available. Next slide. Next one as well. Okay, so here is more of an example of a global Anycast type environment. Next slide. So you can see instead of routers, we're looking at it from the perspective of autonomous system numbers. And what an ASN is when an organization wants to do global routing, they're essentially going to get an ASN from the local router routing registry. And what it is it's simply a number that identifies that organization on the internet. So Comcast is an ASN, AT&T is an ASN, ISC is an ASN. So you essentially get that, and routing is then done through ASNs. And with everything else equal, the shorter number of ASNs is the preferred path. Next slide. So we show you an example where we sort of meld a local environment where we have 2 servers connected to 3 different ASNs to serve the global community. And in this environment, traffic that comes into, for example, say the top 2 servers there, those 2 will be load balanced. But even if that entire site goes offline, there's still ones originated other ASNs that can serve that traffic. So essentially, it's a great way to provide high availability of your Anycasting service. Next slide. So Anycasting with DNS. You can do either recursive or authoritative or both. And there are a number of benefits that are similar to both methods. So obviously, if you're able to distribute Anycasted nodes across a geographic area, like across the world, you're going to reduce your latency to those services. Additionally, you're going to add redundancy as entire sites can go offline, and the recipients will simply transition to the next closest in terms of a network metric. ISC's FROOT service that we operate and SMSPE are 2 examples that we'll get into a little bit. Next slide. So our first poll question. The question is simply, are you Anycasting today? And we have 5 options. Yes, in a private network. Yes, publicly. Yes, Anycasting other services other than DNS. No, or not sure. And we'll take a look at the results a little bit later. Next slide, please. So there are some impacts on protocols that you have to be aware of when working with Anycast, because essentially you have the same source prefix being sourced from multiple locations. So global stateless options work fine, but some things you have to keep in mind, for example, a trace route. So if I, for example, was on our Amsterdam FROOT node, and I was trying to trace back to someone that had reported a connectivity problem, and I was sourcing from that virtual loopback, from that Anycasted address, what I would see is I'd probably see a trace route that seemed to have many holes in it. It would have some stops and starts. And It's a very interesting trace route that you don't normally see, but the reason you might see that is because the ISPs in the return path might not necessarily prefer the Amsterdam F-route node. So essentially, some might, along the way, might prefer London or Frankfurt or so on and so forth. So what will happen is they'll actually do their return back to that node, which won't be expecting the traffic. So the Amsterdam node won't receive it, and thus it looks like a drop in the trace route. But it's actually not a harmful thing. It's just something that you need to keep in mind when doing Anycast on a global scale. Next slide, please. So UDP is typically stateless. It's well suited for Anycast, and typically especially in a DNS environment, the conversations are very short-lived. You simply do a short query, you get your response back, and that's that. And next slide, please. For TCP for DNS, it's typically similar. Typically, the conversations are short-lived, and that works fine. The thing to keep in mind is that long-lived TCP sessions can have issues with Anycast, and so an example is a zone transfer of a large zone. If something were to happen in the middle of the network while you're doing that zone transfer, you can have an issue. We have an illustration kind of show that. Next slide, please. So here's an example of what can happen if you're in the middle of a TCP conversation and some sort of instability causes you to, the end user, to go to a different Anycast instance. Next slide. So after this step is where you have to imagine that something has happened in the network. It could be all sorts of various reasons, especially if you're global, if you're doing Anycast on a global scale where you don't control all the paths. And next slide, please. What will happen is then the ACK data will then go to a different Anycasted instance. And because that bottom server has no idea of the conversation that was occurring to the top server, next slide, it will reset the session. So that's just something to keep in mind for long-lived TCP sessions. And the longer lived the session, the more likely you are to experience some sort of instability that might send you to a different Anycasted instance. Next slide. So operationally, what does this mean? The location of the Anycast servers is important and depends on the network topology configuration. A lot of the pitfalls that we're speaking of in terms of TCP are easily mitigated if you're doing this in a campus or LAN type environment where you control all the paths and you know where things may fail over. It's more of a caveat when you're doing global routing. Next slide, please. Thank you. DNS and Anycast. So like we said earlier, Anycast is a great scheme for adding resiliency and lowering your round trip time for DNS. And the reason, like we said, is it's short-lived and it has a small chance of hitting those longer-lived TCP query issues that we mentioned earlier. And we have some graphical representations of that. Next slide, please. So here, let's imagine this is an ISP. And actually, think back to 10, 15 years ago before Anycast. And at least here in the United States, what large national carriers would do is for their end users, they would typically give out different recursive DNS servers per region. So for example, I live in the Midwest region. They may give me 2 particular DNS servers, but someone that lives out on the West Coast may have 2 different DNS servers. And what could happen easily, and did happen a number of times, is one region would have issues with both of its DNS servers and essentially all of the end users in that particular region, from their perspective, their internet's down because they can't resolve any domains. And there really was no reason for that, because there were other available DNS servers in different regions connected to the same backbone that likely could support the additional queries. So Anycast has really replaced that sort of setup today, and we're essentially, most ISPs now will just give out the same few DNS servers across their entire backbone, and traffic if there's a regional failure of a regional hub or something like that, where DNS servers in one region are down, the end users will simply route around it and go to the next closest DNS Anycast instance. And the end users don't know necessarily. They might see a slightly larger round trip time, just depending on how big of a reroute. Otherwise, it'll be seamless to them. And most ISPs are doing this now today. Next slide, please. So here is another example of, this one's more example of authoritative, because you can do this with recursive. The last one's recursive, this one's more authoritative, but it's the same general principle. Next slide, please. You can see where the requests are coming in and trying to stay as local as possible. And then next slide. You can see we have a POP failure, or for example, instead of being more dramatic and saying failure all the time, we could also just simply say that someone's doing maintenance there, taking down the site, and they want to do maintenance, and seamlessly, next slide please, seamlessly the traffic will route around to another available instance based on the network metrics. Next slide. So here's an example of, next slide. Here's an example of a global type instance, where essentially you're trying to keep traffic as local as possible to the various continents in this particular example. And ISC Froute is an example of this sort of deployment. ISC Froute was the first root letter to Anycast, their root service, and now is Anycasted from over 50 locations around the world. And we have some graphical representations of that soon. Next slide, please. And so, yeah, the first thing we are going to talk about is Froute. So, like I mentioned, Froute was the first Anycast, and we're always interested in deploying more Froute locations, particularly in locations underserved by the current root server deployments. On this map here, you can see all of the locations, and the green ones are ones where we are Anycasting IPv4 and IPv6 today. The blue ones are sites where we're currently Anycasting IPv4 only, and we're always looking to make more of those blue ones green. Next slide, please. So now we're getting into the details of how the particular Froute environment, Anycast environment, is set up. So let's start actually at the bottom with number 3, the global nodes. These are larger nodes. They have significant transit capability. They're usually in large telecom centers that you're familiar hearing, Amsterdam, San Francisco, Chicago, so on. And what these sites do is they announce a /23 for IPv4 and a /47 for IPv6. And the Froute service addresses are within those covering prefixes. And from the global site, we announce this prefix globally. So everyone that has a global routing table should see the /23 and the /47. So then we go to number 2, that contrasts the local nodes, which are typical Froute deployments are at internet exchange points, or occasionally inside an ISP network. And what these do is they announce a more specific prefix, both for IPv4 and IPv6. They announce a /24 for IPv4 and a /48 for IPv6. And it announces those using BGP. There's a BGP community attribute called the BGP no export community. And what that does is that when we send that, it signals our peers to not send that prefix beyond their boundaries. So only our peers see it. It does not get sent farther downstream. And this is an attempt to keep traffic at these local sites local. And then anyone that does not peer with a local site will see the global prefixes. Next slide, please. So here's a great illustration to show how a number of different customers where their traffic may go in terms of some ISP, some ASNs, some ISPs that peer with a local node, some that don't. So next slide. So there's the global prefixes that we were talking about. That's announced globally. So every autonomous system will see those prefixes, the /23 and the /47. Next slide. And then there are the local prefixes we were mentioning. The /24 and /48 with the no export. So next slide. What happens is those two autonomous systems at the left and right that peer with F-root at the local node, they actually, in their routing table, what will happen is they see all four prefixes. They see the global and the local prefixes. But because the local prefixes are a /24 and /48, which are more specific, traffic will get routed to the local node. Next slide. So you can see a representation of that. The local node, since it's more specific, will always be preferred in this particular instance where someone is peering with a local node. Next slide. And for the other autonomous systems that do not peer with a local node, their traffic will be destined to the global node since that is globally viewable. Next slide. So why do we have these three levels? Why do we do this? It's a strong desire to keep traffic local. A number of the F-root local nodes, which make up the majority of F-root, they're in areas that may be constrained in terms of network capacity. They're in developing areas of the world sometimes. And the reason we have these levels is a strong desire to keep too much traffic away from those. We want to try to keep traffic as local as possible. And then have additional traffic that is not peering a local node go to the global nodes since they are well provisioned for that amount of traffic. Additionally, it adds some diversity to the root ecosystem, the root server ecosystem. On purpose, we do things a little bit differently than the other root server operators. We always try to make sure that there is no one attack vector or method of procedure that could cause a cascading of failure across the root system. One issue is this can create some confusion for our peers. So from time to time, we'll get a report from our peers that they're concerned that they get the /24 and /48 with no export. And since the no export community is attached to it, they are not supposed to send that prefix down to their customers, their downstream customers. And they have a concern that their customers won't come through them for F-root, like either they'll be black-holed or they won't prefer it. And really the issue there is that, so anyone peering the global routing table should see the /23 and the /47, the global prefixes. In the case of a downstream ISP that is not peering directly with F-root, essentially they might not see it, but if they send their upstream and their upstream is peering with the local F-root and it does have those more specific prefixes, the traffic will essentially be shortcutted over to there. So it's an interesting scenario where the end user might not see those specific prefixes, but they are still coming into play. Next slide, please. So one of the things that we've been doing is we've been doing a lot of F-root measurements to see where users are getting their traffic from, which Anycast instance are they talking to. And a great way to do this is we've been looking at using RIPE Atlas probes. So RIPE is the regional internet registry in the European region. They also operate a root named Server KRoot, and they have this RIPE Atlas system where essentially what it is they give out a number of little devices. They're about the size of like a home router. And they've been handing them out at conferences, and you can also sign up to maybe get one from their website. And essentially, they ask you to put it in your environment, give it an IP address, and then they have a number of measurements built into these probes. And additionally, users participating in the program can create their own measurements, custom measurements. And one of the measurements that is built in from day one is some measurements to all of the different root server operators. So this map here is simply a map of all of the Atlas probes. There are about 9,000 active ones. Those are the gray ones on that map. The yellow ones are ones that are temporarily not accessible, and the red are ones that have not been online for some time and are considered abandoned. Next slide, please. So Ray Bellis here at ISC, he's our research fellow. Earlier this year, he looked into FROOT performance, and the reason he was looking into it is to see how we were doing today, how we could improve it, and potentially where we may want to look at adding new sites in the future to try to lower the round trip time for DNS requests to the root. And the first thing, this is the first graphical representation that he created here. And what you're seeing is anything over a round trip time of 200 milliseconds is in red. And the first thing that we noticed were a lot of probes in the Western Central European area in red. Next slide, please. And we looked into this further because there are a number of FROOT nodes in that area appearing at very large internet exchange points. So ideally, there should be far fewer of these probing sites in the United States. Like in this case, what we found is a number of probes in Europe were hitting our FROOT instance in Atlanta, Georgia, in the United States. And we took a look at this, and what we found is one of our providers in the United States here, we peer and get transit from them at some locations, and sometimes both at the same location. And in this instance, we were sending the FROOT prefix out both the peering and the transit PGP sessions. And the way that the local preference is set up on this and most other ISP sides is customer is always higher preferred, and then peering is lower than that. So essentially, the transit sessions in the United States are being preferred. So essentially, this was fairly easy to remedy. We just updated the outbound routing policy to not send the FROOT prefix out the transit. And then, next slide, please. Then you no longer see those probes hitting Atlanta. So essentially, this is from the vantage point of the Atlanta nodes. So the reason you see them all disappear from the European region is now they're no longer hitting Atlanta. They distributed to a number of different nodes, such as Amsterdam, Frankfurt, London, Paris, and a couple of others. Next slide, please. Here's an example of a PGP leak. So like we were saying earlier, we send the local nodes. So this is the local node in Santiago, Chile. And essentially, we're sending the FROOT prefix with a no export, and one of our peers was taking the FROOT prefix, and they weren't honoring the no export. So essentially, they leaked and then they additionally leaked the prefix to their upstream network. So a number of ISPs were seeing the more specific /24. In this case, it was IPv4 only leak. And since this 24 is more specific, a lot of nodes in Europe and a few in the United States were preferring this. So next slide, please. I'll show you how I track this down. So what you need to know is that for our FROOT Anycast instances, they all have the same origin autonomous system number, ASN. 3557. So additionally, we also have a unique ASN for each site. We acquire an ASN. We go to the regional internet registry, and each time we're turning up an FROOT node, we get a new unique ASN. And so in this particular example, I bolded them on the right. I grabbed some output from a BGP looking glass from Hurricane Electric. I grabbed them because we peer with them in a number of locations. And this is from their Milan, Italy router. And you can see in the first line there, the 33082, that's our ASN for Frankfurt, Germany. The next one, for example, 30126 is Paris, France. The next one is 25572, which is Madrid, and so on and so forth. So that is what signals to me in terms of a leak where it's coming from. And actually, at the bottom there, this is the actual output I grabbed from our ticket from that leak, that Santiago, Chile leak. So what I did is you can see R all the way on the right there. That's the origin AS. And as the path grows larger, additional ISPs that it's going through are added on the left there. So 3557 on the right is the origin. The 33075 ASN is our ASN for the Santiago, Chile node. So that's immediately what told me where it was coming from. And then the next ASN, the 6471, that's who we peer with there in Santiago, Chile. So that gave me the information I needed to go contact them and have them rectify the issue. Next slide, please. So here's an example of issue where the no export came into play in a different way. So at Internet exchange points, we peer with participants, and sometimes we peer with route servers. So an Internet exchange point is usually just a simply, think of it as like a large layer 2 switch where all the participants join in, get an IP address in the same subnet, and you can either build individual BGP sessions to everyone else on the exchange, or sometimes you can build an IP BGP session to the route server and then get all the prefixes for all the other peers since they do the same. So it's a way of getting up to speed on IXP much easier as opposed to having to contact everyone on the exchange and build BGP sessions individually. So in this particular case, we were announcing our local prefixes out with a no export to the route server. And in this case, the route server itself was acting on the no export. It saw the no export, then it didn't send the local prefixes to any of the participants of the IXP. So in this case, we contacted the IXP and worked out some routing policy so that the route server no longer act upon the no export itself, but instead sent the prefixes out to participants with the no export attached to it. Next slide. And here's the aftermath of that. You can see that now a number of probes in Poland and some in Germany are now using the FROOT instance in Warsaw. Next slide. So here's a vantage point from looking at the probes hitting our FROOT node in Palo Alto, California. And this is close to our ISC headquarters, and this particular FROOT instance is in our main autonomous system number for our corporate network. And at the Palo Alto site, we have a lot of unique private peering sessions to ISPs that don't normally peer, large tier 1s for an example. And this is actually an example of where that can actually have some issues with Anycasting. So we have a number of those large providers where this is the only place we peer with them. And so what was happening is FROOT traffic is obviously going to prefer that shortest path, the shortest ASN hop. And since they're directly connected in that one place, traffic from all over the world was going to come there. So take note of parts of Eastern Europe in this particular graphic, and also parts of the East Coast of the United States. And then let's go to the next slide. And you can see a number of those probes drop off. And essentially what we did is we just went to one of those international carriers, and essentially I opted our route-bound policy, our outbound routing policy, to no longer send the FROOT prefix to them. And essentially this actually improved the service because A number of probes actually are now utilizing sites much closer to them, as opposed to coming internationally to the one site, Palo Alto. Next slide, please. So here is a vantage point of all the probes hitting our Amsterdam global site in the Netherlands. And what I actually want to point out is a number of countries where you actually don't see many probes hitting it. So if you look at Spain, you see a couple. If you look at the Ukraine, there's a few there. And then especially look at the Czech Republic, it does not even look like there was one probe there. So we looked into that a little bit further because it seemed very unlikely that there were no probes in the Czech Republic. And next slide. What we found there is our node in Prague in the Czech Republic is simply so well peered there. The ecosystem, the peering ecosystem is so positive there that essentially they're all using the local node, and none of them are going over to the Amsterdam global node. So this is actually a great example of where the BGP no export for our local nodes is actually working really well. Next slide, please. So SMSPE is another product that we have here. It's a DNS authoritative hosting in Anycast Cloud, and it's available to non-commercial entities such as top-level domains and so on. And the way it works is you'll notice that throughout the presentation, we've been mentioning the global prefix is a /23 for IPv4 and a /48 for IPv6, excuse me, /47 for IPv6. And you'll know that there are two 24s inside of a 23 and two 48 inside of a /47. So you're probably wondering, what do we do with the other half of the global prefix? And this is actually where SMSPE comes into play. So from those global sites that announced out the /23, we also announced out the more specific /24 and /48, other than the one that we use for FROOT. And essentially, we create another Anycast service where essentially we have customers use for secondary for hosting their zones on a global scale, where they might not be able to do that themselves without significant cost. Next slide. So in summary, Anycast is a routing scheme that can be useful in deploying some applications, especially DNS as we've shown here today. There are some protocol level implementations such as traceroute, like we mentioned before, that need to be considered when designing Anycast, but are not issues that really should hold you back from testing. Lots of folks are doing recursive and authoritative Anycast DNS, and you should feel free to try it as well. Next slide, please. We have a number of resources here available. The first link there is a very detailed, essentially design doc for the FROOT Anycast setup. It goes into very detailed protocol level implementations and such. So that may be of interest to you to read. It is an older document. It is from 2004, but really most of what's in there is still valid today and still the method that we're using. The second link there, the YouTube video, that is a presentation that Ray Bellis did at UKNOF. He was the one that created the visual tool to visualize a lot of that Right Atlas probe data. The third link there is the Right Atlas probe site itself. Might interest you to go there and see if that's something you want to do. You can register for a probe potentially, and if you're approved into the program, once you get that, you also get like credits that allow you to create custom measurements using other probes throughout the world. And finally, if you're interested in peering with FROOT, check out our peering DB page, as12a.peerdb.com. Like I said earlier, these are typically deployed at internet exchange points. So you can, at that page, check out where we're deployed at and see if we have any internet exchange points in common. And if so, that page also has contact information for our peering team. So feel free to drop us a note and request peering sessions. Next slide. So we have one final poll question, and that's a simple yes or no. Would you like to see another webinar on Anycasting DNS from ISC? Feel free to drop your answer in there, and we'll check that back a little bit.
All right, thanks a lot, Jason. That was very informative. Don't take much of a break, Jason, because we have some really good questions from this session. So I'm not sure I should have issued that challenge. Right quick, the results from the previous poll. There are 18% of you that are deploying some sort of private Anycast environment right now. 13% of you are doing Anycast on a public deployment, and about 30% are not doing any Anycast deployments, and we had several that did not answer. So, but we'll jump right into the questions. The first one comes from Paul Krager, and I apologize in advance for mispronouncing names. I will certainly do that. But his question is, what mechanism is used to monitor named D to determine if it's up? And I'll actually take this one so Jason can have a little bit of a breath. Yeah, we actually fire off named D via a wrapper script. And if you look in, and I'll go back to this page that has the details. If you look at that technical document that's the ISC Technical Note 2004-1, there's actually an example wrapper script that we use. Now, of course, this is just to determine if named D is up or not. So if named D dies, the script will die and withdraw the route, et cetera, et cetera. But there's certainly more to monitoring than whether or not something is just up or down. So what we usually tell people when they ask us about Anycast is whatever monitoring tool you're using now is probably the one you should stick with, and however you want to react to those alerts is up to your own policies and whatnot. And let's see, I'll find the next question. I also want to say hello to Michael Sinatra. It's good to see you on the WebEx, and Michael actually corrected one of our slides, so kudos to him for that as well. So Bjorn asked, and this is very interesting to me, Jason. I don't know the answer, so we'll see where this goes. But do we have any, or how does Anycast work with, I believe it's MP TCP? So this is multiple TCP connections.
Multipath, yeah.
Yeah. Any experience with that or thoughts on that?
Interesting. So yeah, that is an implementation that is becoming more common. I think some Apple products are actually, they might be using it by default now, or at least it's a toggleable option. Interesting. So in that particular case, you could find yourself heading multiple DNS Anycast instances. I think the question really is it going to, essentially, how is the multipathing going to work? If it's essentially like a flow-based type thing where the entire flow, the entire conversation is going to one Anycast instance, that should be fine, should continue working. If it's at like a per packet type thing, that could be interesting. So I think that's a little bit more on the implementation side of the multipathing TCP, and I'd have to look at the vendor implementations to see how that's being done, because I'm not quite familiar with that, to be honest.
Gotcha. Okay. That's a really good question. Thanks, Bjorn. Paul also asked, zone transfers would have to go to the unicast address to each slave. Is this correct?
Yes, that is one of the items that you will use the unique unicast address for. Yeah.
Yeah. And then Peter Hudak asked, do we have some stats about the number of TCP-enabled queries that we receive at FRoot?
Not offhand, no.
Yeah, I know we keep these, but I don't have an offhand link or where one would find them. So, Peter, we have your contact information. We'll try to follow up with you on that one. Peter also asked, do you use hardware, software diversity? Is there any vendor diversity, DNS software, OS, et cetera, et cetera?
Absolutely. So our specific server hardware for running the FRoot nodes are fairly unique. We have a number of different vendors, and just due to the sheer timeline of how long some of these sites have been out there, some of these hosts are quite older and some are quite newer. And additionally, there is some diversity in terms of networking equipment as well. Different routing vendors and switching vendors are involved. The operating system for FreeRoot is FreeBSD. We're standardized on that particular OS, and that contrasts on purpose to a number of the different root server operators that probably are mostly on Linux-based implementations.
Okay, excellent. John O'Brien asks, what routing protocol or protocols do the FRoot and SMSPE nodes use, and what implementations thereof? For example, Quagga.
Yes, Quagga is actually the routing process that we typically use on the FRoot name servers, and we have a couple of different setups. We have some sites where we peer BGP using Quagga to our routers and announce out. And we have a lot of other sites where we actually do OSPF on these servers, and then in a LAN type setup where we have the servers connected to switches and the switches are connected to a couple of routers. So it's kind of a full mesh, and OSPF is used in that case. And then the routers essentially do redistribution into BGP and send a summary advertisement.
Okay, excellent. And Rhonda McFadden, if you're still around, you had a note in here about possibly needing further explanation of the Santiago ASNs. If you have a more specific question, we may be able to address that if we have time. And Peter Hudak has another question. Which method do you use to identify answering server? ID.server or other method?
Yes, that is, in fact, the ID server query method is one example, and we can actually find that query. Maybe paste it in the chat room for you if they're interested.
Okay, yeah, that would be good.
I'm sure other folks are not familiar with a particular query, but essentially what it does is it requests the name server to essentially identify itself, and trying to find it. Here we go.
Okay, I believe Jason is cutting and pasting a query for you to try out yourselves.
Mm-hmm.
All right. We have a security question that has come in. In order to protect the DNS server, what solutions are you seeing or using? Traditional firewalls, NG firewalls, IP tables, something else?
We have some custom implementations that we probably shouldn't discuss too much.
Right.
But essentially it is software-based.
Gotcha. Let's see. John O'Brien asked, do you announce withdrawal mainly the latter routes automatically based on monitored health and status? If so, have you experienced flapping problems? If not, how do you avoid them?
That is a good question. So we don't do that today, but essentially we just alert on it. But that is a pitfall of creating a health check that automatically withdraws the route. You can find issues with flapping, or you could have issues where essentially the prefix is withdrawn in many locations simultaneously if for some reason you have an issue that hits the health check. So just something to be mindful of. Maybe instead of doing an automatic pull, just have it go to your NACS monitoring system.
Okay, gotcha. Masood asked, how long does it usually take for the route to a local instance dropped, or the route to be dropped in an Anycast setup if a DNS server failed?
That's a good question. It depends exactly on the failure scenario. But if it's something where, say, the server fails, essentially the interface and adjacency will go down within a couple seconds for most of our implementations, and traffic will no longer be destined to that down server.
Gotcha. Okay, Chris Dorsey, and actually we had another question about this as well from Chung. Do we have any concerns over the ongoing maintenance of the Quagga software? And I think, correct me if I'm wrong, Jason, but I believe we've started looking at Bird as well. Not that we have concern over Quagga, it's just looking at some different things.
Yeah, it is always good to have different implementations ready. And historically, we've been using Quagga pretty much across the board for our implementations. But another routing process that has gained a lot of traction recently is Bird, and especially when utilizing BGP. So Quagga is not well known for scaling when using BGP, and a number of extensions have been added, but it still lags, and a number of inter-exchange points, especially in the European theater, the larger ones, for their route servers, which do a lot of peering, they've been starting to transition to Bird, and they find it to be very stable and quick when learning prefixes. So it's something we've looked into, and it's something that the Quagga config is pretty small on most of our effort instances. So it wouldn't be very difficult for us to just drop in Bird instead, and we have been doing some testing on that.
Okay, very good. Bjorn asked, and this sort of relates to a question that we had on the earlier session that I thought was important. Bjorn's specific question is, are you considering to have only V4, IPv4 and IPv6 nodes if there happens to be a specific bug on either version? And I think the question that was posed earlier was, is there any difference in Anycasting IPv4 versus IPv6?
Yeah, let's start there. So no, there's really, from the Anycast perspective, no difference from IPv4 and IPv6. If you have an IPv4 node and you have that address on the loop, that Anycast address on the loopback interface, and you announce that using Quagga, for example, to add IPv6, really, you just add the IPv6 address there onto that virtual loopback interface, and then set up a new either BGP IPv6 session, or you set up OSPF version 3 for IPv6, and essentially you'll just have a separate IPv4 adjacency and IPv6 adjacency, and then it just works. Okay,
very good. Chris Dorsey also asks, what is your typical convergence time?
It depends on the particular setup. If we're talking about a site, let's take an example where an entire site is lost power and gone offline. That will be maximum 3 minutes for convergence, and that is about that. For typical the BGP timers to time out, and that's only in a scenario where our interfaces to our upstream have not gone down, which would be likely in that type of environment. So I would say like maximum 3 minutes, but really in reality, it's probably much, much shorter.
Okay. Chong has submitted a good one because it's one that I think we've heard a lot about. But he asks, is there a setting within Quagga that will let Quagga withdraw the route automatically? We're using expect to withdraw the route manually, and it's ugly. And I've heard that the ugliness part many times. So do you have anything better for him, Jason?
No, there's nothing inherent into Quagga itself to do that. Probably the ideal setup is probably to create really a custom health script to try to pull that. We've tried doing things like shutting down that virtual loopback interface, and we've seen inconsistent results. And expect really is one way of doing it, and not necessarily a bad way if it's reproducible and works for you. But yeah, there's no magic tie-in, unfortunately.
Okay. Bjorn asks, if you're using Anycast within an AS, which is better, internal routing like OSPF or creating a private ASN and use BGP?
Well, making the assumption that you already have an interior gateway protocol such as OSPF set up, it probably is easier just to go ahead and use that as opposed to creating a private ASN using BGP. But really, it probably boils down to just what you're more familiar with. Honestly, in my particular case, I use BGP much more than I do OSPF, so maybe I would do it that way.
Okay, thank you. And then back to Rhonda's question about the Santiago ASNs. What she was after was some additional troubleshooting information. she was following along with your references to the ASNs that led you to identify the particular leak you were talking about. And she thought she heard some ASNs mentioned that she did not see on the slide. And I think Vicki has pulled the slide back up for us now.
Oh, okay. So yeah, I mentioned the 3557 is the origin ASN. The 33075 is our per unique ASN per site. That's the one that identifies it as Santiago, Chile. The 6471 is our peer that we have a BGP session to. And the 27986 is actually another ASN owned by the same peer, likely as part of the acquisition. So essentially that's a local Chilean ISP.
Okay. Excellent. Okay, Rhonda, if that didn't help, then please, okay, she says thank you, so I think we're good on that one. Michael Sinatra also adds that he's found that the if up, if down trick on both Linux and FreeBSD works quite well for inserting and withdrawing routes. Do we know if that also works with Bird?
I imagine it likely would. Bird has some additional details in your configuration where you can actually set up the time to how often it rescans the kernel routing table, and it makes it really easy. I think you can do that with Quagga well, but Quagga hides it. So that'd be something to test, yeah, with Bird. Okay,
excellent. Michael says thank you. And amazingly, we've gotten through all your questions. Those are really, really good questions. Thank you, everyone. And thanks to Jason again for spending the time with us to talk about Anycast. Thank you for joining this ISC webinar, and we hope to be talking to you again in the future. Thanks again.